Thus, we are going to be able to start today's media workshop. With us, to start, we have Robert Meissner, the ESA coordinator, and Paul Fischer, responsible for communications at the ESA. The subject here is Earth seen from space. You know that satellite information is precious and ignores borders between states. For us journalists, it is essential. You need to note that there is a great number of applications with regards to these observations. I give the floor to Mr. Meissner. Mr. Meissner?
Yes, can you hear me?
Yes. We can hear you, Mr. Meissner. It's okay for us.
Okay, great. So, and can you see my slides as well? Because I cannot tell in the moment.
I hope so. Yes, it's okay.
Okay, great. Yes, thank you very much for the invitation to speak here. And also thank you for giving us the opportunity to... I have an echo on my sound here.
We have some echo also, but it's okay.
Now can you hear me?
Yes, you can continue, please.
Okay, now it seems to be better. Okay, I'm coming from the European Space Agency. As many of you are probably aware, we're running and operating and developing satellite missions, which are in this case made for observing our planet, for observing Earth. And as you can see in this slide, in the meanwhile, in the last 15 years, our fleet of satellites has grown. And we're in the moment running 16 missions up in space, and we're planning, we have around 25 to 30, it depends a little bit how you count, in the planning for the next 1 to 2 decades. So there will be a lot of information coming on top of what we already have in space. And that makes it a bit, that poses a challenge for us, because as I've mentioned, or as you've mentioned, I am involved in communication, but mainly what we're doing is we're visualizing the data that we're getting from the satellites. And I wanted to give you a little introduction, first of all, to show you where the challenges are for us, looking at this huge amount of data, but also at this diversity of data that we see. And that's a bit the challenge here, to have the data ready and to go from the raw data into something that people like you can use for your work to report about climate change, but also to report about global change in a more general way. And I'd like to show you with my first slide, with my next slide, that visualization is not new. This is a graph that has been created by Alexander von Humboldt, and it shows the lines of the same temperature. And it is a very early example of visualizing data, but it is also shows that the urge to visualize complex data has already been there a long time ago, and it's actually going back to very old Babylonic maps, which demonstrate that people and we have always tried to generate an image of the world we live in. And we're trying to do the same, but we're facing several challenges, and one of them is that most scientists work with visualizations which are a bit different from what we have in mind. This is just one example of what we typically see in scientific visualization. It's a methane map, but it doesn't matter so much what is shown here. What I wanted to show you is the tendency to use acronyms, the tendency to put as much information into one visualization as you can, and also to show different aspects or different data sets in one visualization. And our task is to make visualizations like this, which are more made for a scientific debate, for scientific discussions, and they're very good for that, but many of them are way too complex to use them as they are. So in a good example, we're facing the fact that we get a visualization and we translate it into something which is easier to grasp and easier to understand. But what we typically get is from our scientists is something like this. What we're looking at is a map of gravity, and understanding the acronyms alone is a challenge, but also turning this into something useful is our challenge. Now, the next example, if we're lucky, we're getting something which goes more into this direction from our satellite, from our scientists, from our colleagues who are working with this, but also what we want to achieve is something completely different. What we want to show is something like this, which is an animation of the gravity field that you have just seen, and it shows basically the true shape of our planet. It's about 10,000 times exaggerated, but it basically shows the influence of gravity on the shape of Earth. And because we are creating images like this, which make a very complex data set easier to grasp, we can achieve something like this. This image made it onto the front page of several newspapers over Europe, or into the science part of these big newspapers. And it demonstrates clearly that we have to work on our side to provide information in a way that makes it easy to use for colleagues like you, for media, for science journalists, for all kinds of other social media, which are very important today. So it's really, the challenge is to face this and to achieve this. Now, that said, just give me a second, please, because I cannot see this.
It's okay, it's okay.
Now, why are we doing this? The objectives are very clear. We want to increase the visibility of our satellite missions, but we also want to communicate about the changes on our planet, because we see these changes every day, and we want to raise the awareness why satellites matter, because they're the only way to get a global picture, to get independent information, to get long-term data sets, and many things we can only measure from space, like sea level rise, like sea surface temperature, changes in land surface temperature, changes of ice cover in the Arctic and Antarctic. So there are many examples where we can use satellites and have almost no other data source, at least not at large, that we get a full global and regular coverage. And of course, for us, it's also important to convince our stakeholders, so they ensure that we can provide long-term data, we can provide 10, 20, 30 years of satellite data to document the changes and to really see if it is a long-term trend or a short-term change in the weather pattern. Because as you're aware, climate is what you expect, weather is what you get, and we have to separate these two signals, looking at the weather and looking at the climate aspects. The channels we use are the traditional communication channels of news, of course, like news, but we're also trying to communicate our messages through events, for example. We have the social media, of course, and we have some dedicated channels like exhibitions and museums whom we work with. The challenges we are facing, one clear challenge for us is the language. We are a European institution, but we have, I think, 14 languages spoken in our member states. And that, of course, makes it more difficult, but it's not only that, it's also the different culture in the different countries. We see clearly that different topics are picked up completely differently in different countries. For example, here in Germany, the environmental topics work very well. Whereas in the UK, for example, I mean, this is a very course, simplification, but it still gives the idea. Economic topics are picked up a lot. The Spanish media like a lot of space topics. It can be technology, but it can also be environmentally. In France, I would say the tendency is a bit more towards the technology topics rather than others. But that, of course, is generalization. I just want to give you the idea of the challenges we are facing. And then we have that I've already mentioned, our challenge to make the complex data, the raw data we get from the satellites, into something usable for a wider audience. And we have a very wide target group. Now, how we're trying to do that, how we're trying to support all these goals and objectives, is we are trying to provide new information, good and, if we can, unique content, which is probably the most challenging one. We are trying to make the data into visuals of high quality, because we're competing with top-class images from photographers and video or cameraman, and the quality is getting better and better. So we have to compete at that level, and that's the challenge we're facing. And the third thing, we are contributing to high-profile or high-interest events wherever we can. But again, the challenges are also here, that we're competing with very high-profile. And I've not advanced my slide here. I'm sorry, I have to look at my PowerPoint because I cannot read the slide here on my side.
Okay.
Okay, now, to give you some examples, this is all the framework, this is what we're doing, why we're doing it. But now I want to, of course, give you some examples and want to show what we're these are some recent examples from the last 2 weeks or 3 weeks, where we have published news which are, to a certain extent, unique or new. The methane emissions over the coast of Mexico have caused a big uproar in the Mexican media. We have historic Greenland ice sheet, where we see the ice melting faster than expected. And we also talk about tipping points. So you can see that the topics are very wide. And other announcements, we've just had 3 weeks ago the Living Planet Symposium in Bonn in Germany with 5,000 participants, looking into all kinds of topics related to climate change, related to Earth observation, and many, many other topics. So these are the classical media news that we publish more or less 2 or 3 times a week, which give people like you the opportunity to follow what is happening in the field of Earth observation, and gives you a little bit of background information, and usually, of course, contains visuals that can be used. And just to give you a little bit of an idea, I've put together a small collection of videos and images for you to better understand where we're coming from. And this first example here is a satellite image which has been taken in April 2019, and it shows the lagoon of Venice with Venice in the middle, and you see all these little tracks of boats, white dots on the circulating around the city of Venice. And if we compare this to an image which has been taken during the first lockdown in 2020, which was very strict in Italy. It's going. You see a completely different Venice lagoon. You see that the water is much clearer because there's much less turbidity, but the main thing that you see is there are no boats around. And this is just an example to show the impact the lockdown in Italy had on the environment, but also on the life of the people. Another example is this one, also again a difference image between before and after the lockdown. In this case, what we're looking at is the concentration of nitrogen dioxide, showing the decrease of, you can say, air pollution. It's a little general, but NO2 is a very good indicator for air pollution. And you see that the NO2 levels dropped by around 50% in all regions all over Europe. And I think that's also quite an impressive visual of this fact. Another example, again, from COVID, India. We're looking at two different points in time again. In 2019 at the top and 2020 at the bottom. And you see, again, these little red peaks show the NO2 concentration. And the little red peaks are decreasing a lot all over India, apart from this area where it says power plants, because the coal power plants, which are concentrated in this northeastern region of India, they had to continue producing electricity, and for that reason, the NO2 levels didn't go down in that region. My next example is focusing a bit more on, first of all, a different technology. We're looking at a radar image here, which has the big advantage that we can look through clouds, and we can also, it works in the dark. And we're looking at Antarctica, and we're looking at the break off of a large iceberg, just as an illustration, as an example, for the changes we're seeing in the Arctic and Antarctic. And as you're aware, it's very far away, it's difficult to get to, it's not very pleasant to be there and work there, but also it's dark half of the year, and it's very often cloud covered. So the radar satellites give us the opportunity to observe the Arctic and Antarctic basically on a daily basis. And it also allows us to have a look at the longer term effects, which this map here illustrates. And again, this map also illustrates something else. We are collecting data and we're making this into something graspable. This data set here goes back into the 1970s, 80s. So all the blue tracks you see on this map show historic iceberg tracks. And of course, changes in these tracks, changes in the speed, changes in the amount of ice, give us an indicator of the change that's going on overall in the region. And as an illustrative element here, we have integrated here the map of a single iceberg, which broke off and drifted for 3 years through the Southern Ocean until it then drifted north and started to melt and disintegrate. And we are I'm showing here another animation which illustrates ice loss in a different way, where we make a relation between the quantity of ice and the size of this amount of ice in comparison, in this case, to the area around New York City. So we use the relation in size to give people a better idea, even though it's still very difficult, of the amount we're talking about. Let me go to the next one, which is very up to date, I would say. And we've just yesterday released an image of land surface temperature. Again, we're looking at a global data set, and we have here 3 examples from recent. The one on the left shows the heat wave in India we had in April of this year. The central one shows an example from the Eastern Mediterranean from last year. And on the right, you see the changes in the ice melt on the Greenland ice sheet. So they're all related to regional heat waves, and we are just about now, in this moment, the colleagues are producing a map of Europe from the last days where we had another heat wave, as you're all very well aware of. Another example is already from 2019, the fires that we had in Australia in 2019-20, so in the summer, in the southern summer in Australia, where we had these huge wildfires, which led also to air pollution across a wide area. And it's not playing on your side, is it?
It's okay for us. It plays.
Okay. Okay. And you see, again, atmospheric data, which plays an important role for understanding the global context. And to complete the picture, we're also focusing on certain regions. We are creating maps, we're creating information from satellite images, and we're trying to make all this usable for the people that are dependent on this. And we also produce, so these were some examples where we created content for a specific event. Now, what we're also doing is, on a weekly basis, we are creating images from our satellite data which illustrate certain regions, certain topics, certain areas, and we publish an image every Friday as an image. As you can see it here, this is a collection of the images we've published, and we do the same for the same area, for the same image. We produce a little video that explains a little bit in depth what you can see there. And if you're interested as a media, we are also providing this image one day earlier, embargoed, so that you have a little bit of time to prepare. So if you're interested in that, please let me know, and we will see that you get the data a day in advance.
May I interrupt you just 5 minutes? You have only 5 minutes, and you have 10 or 9 slides more? I'm sorry. I'm sorry.
Yeah, that's not a problem. I will finish in 5 minutes, no problem.
Okay,
4
because
minutes.
we would like to ask some questions, you know, so if you can.
Okay, I can speed this up a bit.
Thank you.
The next 4 or 5 slides are basically on one topic you may be interested in. The data we have, all of the data actually is freely available and can be accessed by everybody. It has a certain complexity in itself, so it may not be something you may be able to learn how to process in 5 minutes. And this is an example of our data hub, where you can define the area you're interested in and the time range, and you will see the data. But there are other people in the meantime. This is another example on how it works. Like, for example, it is called the Sentinel Playground. It's a data hub which is a bit more intuitive to use, more graphical, and you can also make your own combinations of different band combinations, and you can export the images in different band combinations. And this is something that is very well worth playing around with, and this is something that can be used by a more lay audience who is not used and familiar with processing satellite images every day. And I just wanted to point you to that, because that could be interesting for your work. There is also the NO2 map browser, which allows you to create your own NO2 maps. So changes, as I've shown in the air pollution over Europe, can be created on your own with this browser here. And last not least, I want to briefly say that we are producing a lot of content also for exhibitions. We've just last Friday opened an exhibition close to Torino in northern Italy, on glaciers and mountains, where we contributed. We're actually working on the contribution to the Triennale in Milano in July. And we are this afternoon, I'm going to go to the air show here in Berlin, where we also have an exhibition space where we're promoting climate change as a topic and Earth observation as a tool. And this brings me to the end of my presentation, and I hope I'm on time.
It's perfect.
Thank you very much for your attention.
Thank you very much, Mr. Meissner. I have one question, the first one. Thank you for this presentation. Would it be possible to get a copy of the presented slides? And the question is from Institut Lumière, Matière.
Of course, no problem. Okay. I'm not sure if you will provide it on the website of the forum or if I need
It's okay for the website. It's okay for the website. Okay. Thank you. And another question. Est-ce que vous pouvez nous parler?
Can you tell us about the role of satellites in the water resource management at the global level?
Of water resources?
Yes. Yes, please.
Well, there are many initiatives on that.
Yes.
Simple things include the monitoring of lake levels for power plants. Also related to that, of course, the hydrology of the region, snowfall measures, runoff, melting. It's mainly a topic for larger areas. We're quite active and have some projects going mainly in Africa, Central Africa, but also specifically in the areas where the water situation is a bit difficult, so towards the Sahara to the north from Central Africa and also in Southern Europe. So yes, there are plans for doing that. Also regarding irrigation, you know, we do precision farming works where we guide the farmers, specifically again on large fields, to provide the ideal amount of fertilizer, but also of water to certain areas in a field to minimize the consumption of fertilizer and water and the intake of fertilizer into the ground and the outtake of water. So yes, there are many examples where water management is involved.
Okay, thank you very much. Thank you.
Thank you. Thank you for the invitation.
Thank you, Mr. Meissner. Nous allons continuer donc avec...
We are now going to now switch to our next speaker, Mr. Fischer, who is with us already. I think your microphone is on already. So we're going to start with the first question. First question for you, Mr. Fischer. How the space technology is going to evolve?
Start of my talk.
As you wish.
Let me go into the talk.
Okay.
So yeah, I'm Paul Fisher. I work in the European Space Agency with Rob, specifically in the...
This is for you, sorry.
Backwards and forwards, perfect.
Yeah.
Specifically looking at climate change. So the first slide is... Right, okay. First slide looks at climate data records, but really what I want to talk about is how satellites are going to be helping increasingly support to the Paris Climate Agreement. Of course, climate data records underpin our understanding of the climate. These are long-term data at a global scale for key aspects of the climate. And ESA looks at 23 of a total of 54 variables. So most of the variables that are available to be monitored from space we look at. And they range from variables in the atmosphere, such as greenhouse gas concentrations, aerosols and clouds, which are a major uncertainty in future climate change. The oceans, so sea level rise, salinity, the amount of carbon that's absorbed by marine phytoplankton. On land, we look at land use change, change in forests, etc. And also the world's frozen planets, the CRYOSPHERE. These underpin climate science and climate applications and services that are delivered by organisations such as EUMETSAT and ECMWF. And they help us understand past and present climate. So one example which sort of reiterates one of the images that Rob showed you is we can use these climate data sets to understand how the climate has changed. So this is an example of ice loss across the globe on an annual basis. Satellite surveys have been able to help us understand the rate of change. So annually we're losing 1.3 trillion tonnes of ice each year. That's an ice cube 10 kilometres tall, 10 kilometres wide. It's taller than Mount Everest. It's a massive amount. So we can actually quantify that loss on an annual basis, and we know that it's increasing as well in rate. We also know where the ice is being lost, so mainly glaciers and at ice shelves. So that helps us understand aspects of the climate over the last few decades. Second example relates to sea level. Again, using satellites, we have a really detailed knowledge of how sea level is changing. We know from hundreds of kilometres above that sea level is rising by 3.3 plus or minus 0.4 millimetres a year. And it just blows my mind the accuracy that these satellites can detect change. So we know that it's that sea level is increasing. We know that the rate is accelerating. We also know that sea level is not uniform across the planet. So the graph, the globe on the left-hand side is mean sea level, and we know in certain regions of the world sea level is increasing 3 times higher than other areas. So not only do we understand what's happening with sea level, we understand with satellite data the processes that are contributing to it. And on the right-hand side, there's a graph that's basically showing you the dark blue area is showing thermal expansion and contribution to sea level rise. So as the climate warms, the ocean water warms and expands. We know that through in situ floats and sea surface temperature monitoring. And then we know that the other two drivers are glacier and ice sheet melt. And that matches more or less very closely with the altimetry record. So satellites are helping us understand past climate. Looking forward, satellite observations are also driving climate models that predict future change, and there's just 2 small examples here. The top example is looking at lakes. This is a new data set that we've produced in the last 18 months. It's looking at a basket of variables relating to lakes globally, 2,000 lakes, including surface water temperature. The top left is showing Lake Ontario's surface temperature. And colleagues that I've been working with over the last 2 years have elucidated that lake temperatures have been increasing as a result of human emissions. There's been a really close link developed. And we know for every degree of air temperature warming, we're getting 0.9 degrees increase in lake surface temperature. So we've been using those data to understand what's happened to date, but we can add that to climate models to predict future change. And my colleagues have been looking at the emissions pathways and show that lake surface temperatures are likely to rise over the course of the 21st century. That's going to have problems for freshwater ecosystems and local societies that use those lakes for recreation, food and economy. The second example relates to Arctic sea ice extent. We've been monitoring this since the late 70s, and there's been a decline more or less ever since. Now, this is a product that's being developed alongside or in conjunction with EUMETSAT. Scientists know that Arctic sea extent is linearly related to cumulative carbon dioxide loss. So the more carbon dioxide, there's a linear decline in Arctic sea ice. This is astounding, right? For every tonne of carbon that's emitted, you lose 3 square metres of sea ice. We know that quite clearly. And the world's leading climate modelling groups from a project called the CMIP, Climate Modelling Intercomparison Project, sorry, the acronym escaped me, have used Earth observation data of Arctic sea ice and combined it with emissions and future emissions to predict when Arctic sea ice will disappear. So most of us in the room hopefully will be around by 2050, and that's the date where we expect the Arctic to be ice-free in the summer. So we'll see dramatic changes over the year. And the CMIP group is hosted with us in ESA, and that reflects how important it is for observations and models to work together. The models help to validate and increase the accuracy of future predictions. So I've talked about how climate, Earth observation is helping understand past climate and predict future. A major focus of our attention now is to, as well as continue developing the data records so that they get more accurate and longer, is to support the Paris Agreement. So how are we going to help address the climate challenge that we have in front of us? And we do have a challenge, and the graph on the left-hand side I came across almost by accident after the event, and it struck me how big the challenge is that we have. So just to explain the graph, we have years from 2010 to 2060 along the bottom, and the y-axis is gigatons of carbon dioxide equivalent. And the yellow line is an emissions pathway if we do nothing, sort of the business as usual. The red triangle that you can see is the NDCs, and that's the national contribution of emissions reductions through to 2030. So if we implement all those, that's where the emission pathway will go. And then the three blue lines are what we actually need to do to get to 1.5. That struck me in the face that there's a massive challenge where we are. Even if countries do what we're supposed to do, we're getting not particularly close to where we need to be to stay at 1.5. So by 2030, we need to reduce emissions globally by 45%. That's huge. Anyway, so there's a big challenge. Fortunately, the Paris Agreement should help us work our way out of it. So there's something called the Paris Ambition Cycle. So that's the diagram on the right-hand side. So top right, we have the global stock take, a global review of emissions to see where we are, a stock take in terms of meeting the Paris agreements. The first global stock take's finishing next year. There'll be some global recommendations that will help countries where actions take place to reduce their emissions. All countries such as France, the UK, etc., need to take mitigation and adaptation actions to reduce emissions, and then the report to the UNFCCC, and that feeds back into the same loop. So year on year, we should be increasing our ambition to make more changes to deliver the carbon reductions that we need. Earth observations can support three of these main areas: the global stock take, mitigation and adaptation, and the reporting, and that's what I'm going to focus on now. So mitigation, carbon reductions, that's what we really need to do. And satellites are helping to identify opportunities to mitigate carbon dioxide and methane. So we've been able to track atmospheric greenhouse gases for decades, and we have long-term data records. The newer satellites, and this is one example, Copernicus Sentinel 5P, can differentiate between natural sources and anthropogenic emissions at high resolution. So we can pinpoint where those emission sources are coming from. And there's two examples on the right hand of the slide. One of them is a plume of methane from a gas pipe, and the far right image is methane emissions from a landfill site. So we can identify where those emissions are coming from, do something about it, and at a national scale we can track the policies that are trying to make those reductions come to realisation. We have a mission being launched in 2025 called CO2M. This mission is doing the same as Sentinel 5P, but as the name suggests, it's focusing on CO2, carbon dioxide. So as well as mitigating or supporting and identifying opportunities to reduce methane emissions, we'll soon be able to do the same with CO2. CO2 that mission is part of a monitoring and verification project that is being delivered through Copernicus and involves partners such as the EU Commission, EUMETSAT and ECMWF. So that's mitigation. Adaptation's trickier in that there aren't global targets on how the world or how countries should adapt, and there aren't common indicators. So it's in its infancy, and it's complicated by the fact that you need biophysical information that can be provided by Earth observation, but highly local information, the economic, social information, for example. So it's in its infancy, but here's one example related to the urban environment where colleagues in the University of Leicester have looked at the issue of urban heat maps. So many of you in the room will have experienced a heat wave just now. Heat waves in urban environments are worse than they are in rural settings, and that's set to get worse with increasing climate change. We can track urban temperatures with land surface temperature, and we have a mission being launched soon called LSTM, which will provide high resolution data. This will map the temperature in cities, and combined with humidity information, the middle slide, one can work and develop a thermal discomfort index, so how uncomfortable humans perceive that temperature. That means that we can track where the uncomfortable areas are in the city and track the progress of adaptation measures such as urban greening. So what we're hoping is that this tool will help guide managers of cities and urban planners to locate trees and parks, and hopefully that will reduce the hotter, more uncomfortable areas in cities going forward. So we've covered mitigation adaptation. This video, which I think I'm going to try and start. Good. Is looking at counting carbon. So we've covered climate data records. That helps us understand the physical state of the climate. We can see how satellites can help mitigate greenhouse gases. There's an emerging opportunity to support adaptation. Satellites are helping to define the carbon budget, the amount of remaining emissions we have before we reach 1.5. So the jug on the left-hand side is showing how emissions are filling up towards 100%. And this shows that we have 17% of the carbon budget left. That's equivalent to about 10 years of emissions at current rates. Countries can report their greenhouse gas emissions on a national basis in a bottom-up way. So they basically use bookkeeping to estimate emissions on a national basis by looking at the amount of sectoral activity. So how many emissions come from agriculture, energy, waste, etc. But with satellites, we can also look at atmospheric greenhouse gases in a top-down approach. So we can get a global view and then combine it with other Earth observation data. So we can look at the emissions, and then we can look at the carbon sinks, the carbon stocks. So for example, we can look at land use and land use change, which is approximately 25% of global emissions. We have really good data sets at 100 metre resolution of above ground biomass, basically the carbon in forests. We can estimate that as well. And of course we look at wildfires, which then releases a lot of that carbon back into the atmosphere. So that's land. And then we can also look at the carbon sink in the oceans, the marine phytoplankton that suck carbon out of the atmosphere. So we can combine the atmospheric emissions and the measurements of the sinks to estimate the net emissions in the atmosphere. We can look at the fluxes between the atmosphere and the land to help work out what the net carbon budget is. And that helps understand where we are at in terms of available emissions and what we need to do in terms of reducing emissions going forward. So that helps with the global stock take. So that's the global view. The third element I mentioned on one of my earlier slides was how can we support nations with reporting to the UNFCCC. So a lot of the climate action is undertaken, or all of the climate action is undertaken at the national level. They're the bodies that are responsible for reducing emissions. Yearly, they report all their net greenhouse gas emissions and removals by sinks through greenhouse gas inventories. And this is a bottom-up approach where they basically take sectoral activity and multiply it by emissions factors to get an estimate of their emissions. The IPCC has asked for independent measurements to be taken to act as a quality check on those bottom-up inventories. And this is where Earth observation comes in. And we've been working with colleagues in the ESA Recap project using the methods from the animation before. So they're taking data on atmospheric greenhouse gases to estimate emissions. They're looking at all the quantification of carbon sinks to estimate the removals from the atmosphere and combining it with a model to estimate greenhouse gas balance at a country level. So that study was released earlier this year, and the positive news is that models and the top-down atmospheric estimates match. And that helps improve consistency and identify sources of uncertainty, so we can get a true picture of how we are progressing going forward. There were two areas where there was uncertainty that were highlighted. So on the left-hand side looks at greenhouse gas emissions, and where countries are extracting lots of fossil fuel, they're consistently underreporting methane emissions. So that's something that we'll address in the inventory methodology. And on a positive note, I guess, Northern Hemisphere countries such as Canada are significantly underreporting the amount of carbon stored in the carbon sink. So these data are helping with reporting so that national reports reflect the true picture. And as more satellites come on board, this will get more and more refined to increase accuracy. Part of the reporting relates to AFOLU, so agriculture, forestry and other land use change. And as we've already said, we have data sets looking at forestry and land use change. It's particularly important for developing countries who don't have the resources to develop their bottom-up inventories. So they use freely available data, such as Landsat and Sentinel data, to work out their national forestry emissions. And the right-hand side GIF really gives you an idea of how far we're getting now. So this is a prototype scientific study that's looking at carbon losses at a really, really local level. It's based in the Congo, and you can almost see the paths where you've got logging on the left-hand side, and you can compare it to the emissions from smallholder agriculture. So that's helping developing countries with forestry get a really good, accurate estimate of their emissions. So where does it leave us with communication? So for me, the way that Earth observation is developing is showing that the information is becoming definitely more local as the resolution increases. That gives an opportunity to personalise stories and really pull on the heartstrings of the audience. What I'm showing on this particular slide is a freely available web app that allows members of the public to access global data sets and play with... Do you know how I get that to start again?
It's okay? You want to stop it?
It's all right, I've done it. Have I? Yeah, and is that restarting? Yes, it is. Yeah, so you can look at the global data sets. You can explore how, say, land use change has changed over the years, how ozone has changed. you can interact and compare different variables, but what we've done is we've added lots of stories so we can use a narrative to explain what's happening with the climate and how we're starting to help address it from satellites. And I think I'm going to stop there. If anybody has any questions, please do ask.
Yes. So you have the first one. I already asked you if you want to. We can talk about it now. What's the role of satellites in the management of water resources in a global scale? But you already talked about.
So Rob talked about that. The one thing that came to mind was there's a new mission called Land Surface Temperature, LSTM, Land Surface Temperature Mission. That's providing land surface temperatures in really high resolution. So it's giving a global picture every 1 or 3 days. The resolution is within 50 metres, so it's at the field scale. If you can estimate land surface temperature, you can predict heat stress in crops without. You can't see it with the human eye, but you can predict heat stress in a crop. So that's really going to help with agricultural irrigation management, particularly when water is going to become more scarce and heat waves more severe.
Okay. Another question. Quelle est l'évolution du Gulf Stream avec la fonte des...
What is the evolution of the Gulf Stream with the ice melt?
Over there on that computer that illustrates the sort of data that's helping to understand what's going on there. So as I was saying in my first slide, we look at several climate data records. For example, sea surface temperature, ice sheets, sea surface salinity. All of those aspects contribute to the development of the Gulf Stream, or the continuation of it. With ice sheets, melting weakens the Gulf Stream. So all those data are being used to track the Gulf Stream and are added to models of the Gulf Stream to see the long-term evolution going forward in terms of modelling.
Je crois qu'on a une question ici.
We have a question here in the audience with a microphone. Please give your name. Geneviève Del Sol, ex-Météo France. Can you speak in French? I can understand, but very slowly. So, the situation in Ukraine is upsetting all of the forecasts that were made with regards to the Paris Agreement. We see that the CEO of Total Energy is answering short-term questions. There is exploration in the North Sea, and I won't speak of Germany, which will continue to use coal plants, and not even mention Poland, which has never said it would stop using coal. I would like to know whether all of these short-term data are going to change your forecasts. So she's repeating in English.
That information will be noted, will change your point of view and observation.
I don't want to get too political.
No politics.
But carbon doesn't understand politics, and carbon emitted in Ukraine or in Argentina or in Central Africa and goes into the atmosphere still causes forcing, it still warms the planet. So carbon dioxide doesn't get involved in climate change. The political difficulties that the world is experiencing are, of course, going to complicate the ability to reduce emissions. And I think one of the most impressive things that I've seen globally are the number of countries that have signed up to the Paris Agreement. So more or less every country has signed up to make those emissions come to realisation. I don't want to get political. The war complicates things, of course, but we can still monitor the emissions and the sinks, so we know what we need to do. It's then from the scientific point of view and the political point of view to then decide how we go about making those changes. Earth observation can observe those changes and provide the information. How that's realised is probably a bigger question than I personally can answer, I think. It's political will at the end of the day. Sorry.
Mr. Meissner, you are with us? Can you hear us?
I can hear you.
You can hear us? It's okay? So,
Yes, I can hear you well.
do you want to say something concerning this question and war in Ukraine and some changes in the future?
Well, I mean, we have a lot of changes going on, as everybody's aware of. I can just emphasize what Paul already started to mention, that we're observing, we're providing the hard facts on climate, on everything that's happening on our planet that we can observe from space. And as I already mentioned before, the vantage point from 800 kilometers mainly above our planet, where the satellites fly, is a unique way of observing our planet, because it is far away, but it gives us the overview, and it gives us data for every point on our planet on a daily basis. It's always from the same instruments, so you can compare the data also on a longer term. So it's not biased, it's not in an ideal world, of course, but it's always from the same source. It's comparable, it's regular, and it's global, and that's a big advantage. And that's our contribution to, and we are trying to contribute wherever we can and wherever our data can make a difference.
Okay, thank you. On a une autre question.
Another question?
To thank you for your presentation and tell you how useful these satellite images are in our job. For example, a few months ago, I did a report about methane emissions throughout the world, and it was really based on the maps, you know, the Copernicus images you just showed us. So I think we can do more, we can do better, because I wasn't aware of, you know, all the images you just showed, but it's definitely very useful as journalists, especially television journalists, to show you know, the audience how, you know, big, you know, these issues are. Thank you.
Thank you. A lot of that's down to Rob and his team. If you want to come and see me, I'll show you some of the information provided on the computer. Rob, sorry.
And I can contribute to that maybe a bit. Of course, you're welcome to contact us should you have any specific requirements or questions. And I would also advise you to go to the ESA.int website. There is what we call Space in Videos and Space in Images, which is a very large database of material, also on topics which I have not mentioned, of course, also some historic stuff. So there's a lot of material out there on our website as well. But if you have a specific request or requirement, please let us know and we will try to see what we can do.
Merci beaucoup. En tout cas, c'était très riche, très intéressant. Thank you.
Thank you very much. This was interesting and rich.
Tout ce que
I'd like to inform all of you that these presentations will be available on the event site in a couple of days for everyone.
Thank you very much. You are tired. Thank you.